Okay, I wanted to start today with so the plan for today is to cover a few examples of scattering mechanisms, impurities, phonons, all kinds of phonons, polar optical phonon, acoustic phonons and such, and essentially to see their effect on the transport properties of electrons. So essentially this quantum mechanical treatment of scattering mechanisms. And for that we have developed the whole machinery of Boltzmann transport equation that tells us that if I have an equilibrium distribution of electrons, which is the Fermi-Dirac distribution, and I apply an electric field and the electrons start moving, so in the K space the distribution function drifts from a Fermi-Dirac symmetric function to something that breaks that symmetry, and as a result of that the distribution function has an asymmetric part, and that asymmetric part is what gives you the current. That was the idea. And all the microscopic processes of scattering, no matter due to neutral impurities or phonons or charged impurities, dislocations, are buried inside this sort of scattering rate which comes from the golden rule. That was the basic, kind of formalism. And I want to start with a couple of very simple, very simple-minded, not so much of demonstration as calculations of the solution of the Boltzmann transport equation. And here, what I'm showing, just to be kind of get an order of magnitude of things. For example, if I have electrons in a solid that are in equilibrium with a lattice, and the lattice temperature is say 300 Kelvin, then depending upon the effective mass of the electrons, there is a certain wavelength associated with this, which is the de Broglie wavelength, or I think we know the one of the building blocks of quantum mechanics is the wavelength is related to the momentum, right, through this relation, and the momentum is related to energy. So if we assume that the momentum, the kinetic energy is of the order of the lattice constant because it's in equilibrium, the electrons are colliding with the lattice, let's say approximately, then the wavelength is clearly just that. And essentially that's what we are plotting, that if your effective mass of the electrons is let's say it's 0.05, then the wavelength at room temperature is about 35 nanometers, 35 nanometer wavelength roughly. So if you have structures that are microns long, then the particle kind of behaves as a classical particle. It's not affected so much by the boundary conditions. But if you have quantum wells that are, say, 10 nanometer or 5 nanometer, then these are strongly quantized because you are below the de Broglie wavelength of the electron now. So, on the other hand, if you have much heavier effective mass, like 0.4, then the de Broglie wavelength is obviously shorter, about 12 nanometer or so. That means to confine, to quantum confine, heavier carriers, your dimensions must change, and I think it intuitively should also make sense that lighter particles, have longer wavelengths, and heavier particles, effective mass being heavy, has shorter wavelengths. Now, the Fermi-Dirac distribution obviously has the whole everything in it, effective mass and all that are buried inside, because the total energy is conduction band energy plus this whole, potential energy. I'm plotting here just for a two-dimensional system with kx and ky, but I'm just plotting, this plot is against kx, and this is the distribution function, the occupation function, and at all kx for ky is equal to 0, so you're just taking a slice through the kx ky plane. And again, I mean, this is just the Fermi-Dirac distribution, so there's nothing very interesting other than at finite temperatures of 500 Kelvin, there's a certain spread to the carrier distribution in K space. Very importantly, it's symmetric, right? And then obviously as you lower the temperature, it becomes more and more like a step function, right? I mean, that's the nature of a Fermi-Dirac distribution, and I think I think it's very important to appreciate that this is very much due to the Pauli exclusion principle. All this stuff is because of the Pauli exclusion principle. So this is not what happens for classical particles. Okay. Now, in 2 dimensions, if you look at both kx and ky, it's very, very similar. It's basically symmetric, right? This whole picture looks symmetric, and then it will, go from a thermally averaged, smooth edges to very sharp edges as you go to low temperatures, and it becomes more like a cylinder. Just the distribution function is 1 inside the Fermi circle, and it's 0 outside. Right? So it's very straightforward. Now, the interesting question is when you apply an electric field and you turn on this perturbation, which is what we are doing now through scattering events. Basically, we have applied an electric field, and this thing has now drifted to the right, right? This thing has drifted, and now we are plotting that. And we're plotting this shifted distribution function, which is a solution to the Boltzmann transport equation. So we're plotting this function now, f, which is the Fermi-Dirac and the shifted part. And the shifted part, is for example, for a certain scattering rate. This is, you can see. I mean, it is shifted by a certain amount, and as you lower the temperature, obviously again it becomes rectangular, but it's still shifted now by this thing that by an amount that is proportional to the scattering time. That is related to the order of the shift is remember h bar dk over dt is the electric field, right? But then we also add a scattering time to it, right? This is the damping force and all that. And when you reach steady state, it kind of locks and doesn't change anymore. That goes to 0. So the amount of shift in K space is of the order of the electric force. You can write it as Q times electric field times tau m over h bar. Right? That's the order of shift of this. Right? Does that make sense? I mean, just order of magnitude. So if you know your scattering rate is a picosecond, you can calculate how much is the shift from here. Right? If your field is 10 kilovolts per centimeter, you can just calculate it. And okay, so it's a simple simulations, and this just shifted cylinder. And now the more interesting thing is what is the meaning of these rates? What is the meaning of this tau? If I turn off the electric field at time t is equal to 0, if I turn the field off, then I think you can see from this rate equation that it's very clear that if I turn it off at time t is equal to 0, basically this term goes to 0. So I want to track the dynamics of it now, right? And you can see all the k's, k of t will go as k of 0 times e to the power minus t over tau m. It will go to back to its equilibrium value with a time constant of this nature, right? From this equation. So it's a first-rate differential equation. This is not the exact equation. It goes back to its original, but the time rate of change is this. Right? So that much you can see, and that you can obviously also simulate. And I think I wanted to show this because if you look at the Fermi-Dirac distribution at room temperature, at high temperatures, you can kind of see it will just gradually kind of go back there. Exponential decay, right, to its equilibrium value, right, when you turn off the field. But what's very interesting is you can imagine how what is physically going on is the electrons that are here. There are obviously quite a bit of electrons here, and so essentially these electrons cannot really scatter too much into these states because these states are already occupied. They have to kind of scatter all the way to this side because there's some open space here, right? Because of exclusion principle. And that thing actually becomes much clearer if you go to a low temperature, because at low temperature you will see that the distribution function changes in a very interesting way. Basically what you happen is backscatter. You kind of, you take this bunch of electrons and this scatter here, because these things are all Pauli blocked, you can't scatter. So that's the nature of this scattering events. And again, I've not done anything fancy here, just taken the Fermi-Dirac distribution and shifted the k, and then I'm relaxing it back with this time constant. And that's physically what happens in a scattering event, really, right? So, in scattering events. And okay, and you can do that for the 2D too. Now, as you may imagine, the transport is kind of an important statement. Transport is, at least in condensed matter physics, the language that's spoken is that transport is a Fermi surface property, meaning all the transport is occurring at the surface of the Fermi, of the K space, not inside. It's not a bulk property in the Fermi surface, but it's a surface property. And does that make sense? I mean, you can see why. Because in the bulk, these things, you can't do much to them. I mean, they're already occupied. It's just like, the transport on the surface of an ocean is really a surface property too. It's kind of not that dependent on what's going on the ocean floor. It's really screened in some sense, right? So, and here it's and that becomes very clear if you look at the final solution we had for Boltzmann transport equation. What you have here is the asymmetric part, which gives you the current, is dependent on the derivative df over dE or df by dk. Is dependent on the gradient of the distribution function, not so much on the value itself, because this term will just integrate to 0. It's symmetric, right? When you calculate current, it's only this term that gives you the net current. And so, that part, if you look at the derivative in K space, I think, for example, this is the derivative of the distribution function in K space, and at room temperature, it looks like, it doesn't look, so these are the two Fermi surfaces, if you might. At room temperature, it's a little diffuse, but the derivative term, which is a strength of your states, or states that actually give you transport or conductivity, a little bit here and a little bit there. These are the two Fermi surfaces. It's not quite right because you actually have a circle, a whole revolution. It's a kx, ky as well. And in 3 dimensions, it's a sphere, or surface of a sphere. That's where the transport occurs. And at low temperatures, it becomes very clear. This is just a derivative, and it really becomes two delta functions basically. At low temperatures, the width of this is just kt roughly. So it becomes very sharp, and as a result, the transport, the transport is occurring by k states here and here. And nothing is really, these things are not really contributing. They are contributing in the sense they are canceling each other out exactly, these states. Okay, so is that clear? Any questions at this point? Yeah. All right. So if not, let's move on now to a description of some of these microscopic processes of scattering individually. Again, the general scheme of thing is you do the hard work, set up the Boltzmann transport equation this way, and now we kind of want to know what are the scattering rates to actually do the numbers. You are also solving a part of this in your assignment, current assignment problems. Again, written it all over again here, and then this is the distribution function that goes into our expression that the generalized expression we have derived for the current, right? And the velocity here is the group velocity that does not depend on the Boltzmann transport equation. That is just the band structure, EK diagram of the solid. It doesn't care about the Fermi function, and the Fermi function tells you which states are occupied and which states are not. And I think you can see that you're doing this in the assignment, so I'm not going to kind of repeat this. But when you plug this in here, the symmetric part of it will give you a 0, right? Because this is symmetric, group velocity is symmetric, and this is also symmetric, and so that means and they're equally positive and negative in for plus and minus case, so it will give you a 0. Right? Whereas this part will survive, and that's what is going to give you your transport current here. Right? And there is a scattering rate there, and when you kind of pull that all of those out, you will get the current. You can write it as electron charge times carrier density times this whole thing sitting inside here, which is related to your tau m, which is the momentum scattering rate. And then there's the electric field that's driving all this stuff. Charge times field is the force sitting out here. So you have current density is En times field times a number, and I think we have seen already if current density can be written as charge times carrier density times a velocity, and the velocity here is a constant times the field, and so this is what we're calling as the mobility now. So it's kind of and here essentially you're doing an average over all k states or all energy states. I personally prefer the k states, but many books and all have used the energy format, which is fine. Either way, you can do it either way. And you have your important derivative sitting here. On the other hand, so if you calculate the carrier density is just an integral of f of k. There is no velocity involved, right? And then this part cancels out. Carrier density only depends on this part. Right? Does it make sense? You're not changing the carrier density with this picture. Okay, so and then so this is the method to calculate the mobility, and this is written in a generalized dimensions. So if you are in 3 dimensions, 2 or 1 dimension, the d is the dimensionality, 3, 2 or 1 the integer, and there's a density of states related thing here, and you can just I think I've asked you to also just work it out a little. Okay. Question or no? Okay. So the game now, I guess I'm repeating this a little bit, but so we also defined in the last class 2 kinds of scattering rates: a momentum scattering rate where there's a cosine theta factor, which weights. You pay a much more penalty for back scattering compared to small angle forward scattering. So there's because that's kind of more responsible for the transport. There's if you have if you disregard the angle dependence and you just say that my electron was in this k state and it scattered, all I want to know is how often is it scattering without regard to what angle it's scattering by. That is what's called the quantum scattering rate. This is the related to this dephasing or quantum dephasing of if you have a coherent beam of electrons, how much time are they going to remain coherent, or they're going to lose their coherence if a coherent beam, where you have a certain phase relationship between various k states and they're injected, and then you allow scattering around this. It will take roughly tau q seconds or picoseconds for them to dephase, lose their quantum memory, if you might, the coherence of the waves. Whereas this is a very much of a transport thing, so it's and the ratio of them can tell you what sort of scattering mechanism do you have, and that will become clear very soon. One of the things you can see is if the scattering rate is not dependent on the angle, if it's as isotropic scattering, then these two become equal. If it's isotropic scattering, and the reason for that is very interesting. See, when you're summing over k prime, you are really integrating over all k space. Think about 2D or 3D. And a cosine theta function, when you integrate over all 3D or 2D space, you go to 0. When you integrate it, right? It goes through equal positive and negative. Whereas if you have anisotropic scattering, which favors small angles and all that, then they'll have another theta factor here, function of theta, and then it will be non-zero. And we'll see one of the most anisotropic scattering mechanism would be Coulomb or charged impurity scattering, because it's long range, Coulomb potential. So we'll see that charged impurity scattering, Coulombic scattering, will have a large difference in the ratio, meaning these two will be very different. Whereas if you have things like point scatterers, they don't care what angle you are incident at, and for them these two will be equal. So the ratio of the quantum and the momentum scattering rates will be very close to 1. And these two terms are experimentally accessible. When we talk about things like quantum Hall and such things, I think next week, we will show how these are measured. These are directly measurable experimentally, both the times and the ratio, such things. Okay, so let's look at a few of these conventional sort of scattering mechanisms. I'm going to discuss a little bit about some of the isotropic, point defects and charge impurities. But a general principle would be that a static, time invariant, meaning things that not oscillating in time, a static periodic potential will cause no scattering. if you have a static periodic potential, then that is a part of the band structure. That went into the crystal potential. It's a periodic static, potential. And every other kind will cause scattering. So periodic non-static potentials, meaning you have a periodic potential, but it's time varying, and those are phonons, or those are light waves, photons. They will interact with electrons and change their k values. And static non-periodic potentials are obviously defects and impurities that are sitting there in a site. They're not moving around, and they also cause scattering. Okay, and our goal is kind of to explain something like this, which you are doing also in your assignment. There's experimentally measured mobilities, and we are essentially trying to explain why does it have this sort of feature. This is just one example. In many other cases, you have different varieties and all that. And what we want to do is understand a few of these things, calculate them, quantitatively. Okay. So the method would be mobility in a very, very clean or defect-free sample. Semiconductor, for example, or metal is limited by phonon scattering, combination of optical and acoustic phonons. And on the other hand, if you have a very defective sample, high levels of impurities that exceed that of phonons, they will determine the mobility. Now, with defects, you can't really change them easily, but one of the things you can change is phonons very easily by just lowering the temperature. Right? You lower the temperature, and the polar optical phonon freezes out. Acoustic phonon, they all freeze out. Impurities may not change much, but impurity scattering is changing, but not the impurity density typically. So that's a very nice knob to be able to piece apart which scattering mechanisms are dominating and which ones are not. And the game plan is really that find the scattering rate due to each kind of defect, and then the total scattering rate is the sum of all. And whichever dominates is one that limits your mobility at that temperature. Does that make sense? The one which is the fastest or the highest scattering rate. Okay, so I'll skip a couple of things here. And in pictures, before we do the calculations, what we really have to do is, as the electron moves, say in the conduction band of a semiconductor, is the band gap and the valence band. We have to determine what is the scattering potential W of R, then use it in Fermi's golden rule to evaluate the single particle scattering rate using this sort of thing. Remember, some of the nice things we developed for it. For example, we found that this potential is a Fourier transform of the real space scattering potential, right? When we find a matrix element. And also, we found that if your scattering is occurring within the same band, you can forget about this periodic part of the block function. You can just deal with the envelope function, which is slowly varying part. Right? We derived that explicitly, and which makes life very easy because you don't have to bother about that part of it. And then you kind of use the golden rule now and find your tau, use it in Boltzmann transport equation, and get your total current. So this is the whole method for most transport under diffusive conditions. Okay, so I will start by giving a kind of a summary of where we will end up after doing some of these things. For example, the scattering rates. We have also written down that the scattering rate is given by as given by the golden rule is 1 over tau, from k to k prime. Is 2 pi over the Planck's constant. This k scattering potential k prime whole squared, and then you have your Dirac delta function that conserves the energy, say final minus initial, and plus minus h bar omega, where I'm accounting for the fact that there may be phonon absorption or phonon emission as well. And when you sum this to find the total scattering rate of any state k in the electronic band structure, let's say this is your k state, right? And that's your, say, k prime. Let's say your scattering is occurring from here to here. Right? And I'm trying to find the total scattering rate. I sum over k prime, right? Sum over all possible k primes, scattering from here to there, all possible values. Right? if that is not allowed because of energy conservation, the delta function will take care of that. Meaning, depending upon whether it's optical phonon or Coulomb or whatever, if it's elastic, inelastic, this is what's going to take care of it. But no matter what, I mean, when you sum it, when you sum over these delta functions, what you end up getting is this is going to always be in this fashion. It will be 2 pi by h bar, a certain matrix element sort of thing squared. That depends on k, obviously, because you're finding a function of k, times the density of states of the original state plus minus h bar omega that appears. I think you can probably see it because you're summing over delta functions. You are just counting how many states there are, to scatter into, right? And so and it gets shifted by plus minus h bar omega because because of the direct delta function here. It's shifted by that much. This is a very general relation. I think it's very useful to remember it because and probably hopefully it's intuitive. It's just saying that the scattering rate is proportional to the density of states into which you can scatter, and that makes sense. I mean that's the final number of states available to me, and the whether it's allowed or not, the strength or the amplitude of each of these is given by the matrix element. That is the coupling strength of going from initial to final value. Okay? And this is shown from realistic calculations. What we will see, for example, is here's what's called acoustic deformation potential. Acoustic deformation potential scattering is a phonon scattering of the acoustic phonon kind. And that acoustic phonons have a zero energy threshold. We are going to derive it now. As a result, the h bar omega starts from 0. You kind of start from 0. And the density of states for 3D systems is kind of square root of energy, so that's how it looks. So, on the other hand, an optical deformation potential is an optical phonon that has a certain threshold. Optical phonon has an energy minimum of h bar omega naught, so it takes at least this much. And this is the total optical deformation potential scattering rate, which includes emission and absorption, both. Now, remember one of the things we had discussed earlier, that an electron, if it doesn't have at least the energy of the phonon, it cannot emit one. So that's why there's a sharp threshold, and that part is emission. But it can always absorb one. There's no problem, right? And then so this is the absorption rate. This is the emission, and the sum of them is the total scattering rate. And this is kind of a general trend for phonons. For optical deformation, acoustic deformation potential, they're increasing. Here's what's called polar optical phonon. We're going to talk about that a little bit as well. And I think now you can identify this is the threshold of polar optical phonon energy. This is the emission, and that's the absorption rate. And polar optical phonon, we'll see, will decrease with slightly with increasing energy, whereas the acoustic phonons will increase with increasing energy. Here's the ionized impurity scattering. It decreases with increasing energy. I said it's proportional to density of states. So density of states is increasing, but then what we'll see is because of this angle averaging and heavy weighting of small angle scattering, it ends up being that higher is the energy, less is the impurity scattering rate. And I think intuitively, perhaps it also makes sense that if your electrons are moving very fast, they are not really perturbed by charged impurity scattering. Phonons, it's different, because if you have a lot of energy, you can excite a lot of phonon modes. So you can, emit a lot of phonon modes. So phonon scattering polar optical phonon can just slightly decrease, almost constant actually. Yeah. And here's these are the general trends. And here's an example for gallium arsenide, and you can see everything combined. Acoustic phonons, optical phonons, impurities, everything combined. Here's the scattering rate as a function of electron energy in the conduction band. You can calculate the whole thing. And rate, at about say 0.1 eV. Here's a threshold for optical phonon. You can measure your optical phonon energy this way. It's 36 millielectron volts for gallium arsenide. For gallium nitride, it would be almost 100, 92 MeV. So the threshold is a little bit to the right. And silicon is up there. What you see is the order of magnitude is 10 to the power 13 inverse, seconds. So that's roughly 0.1 picosecond. 0.1 picosecond, roughly tau, the lifetime we're talking about here, 0.1 picosecond, after everything is, kind of summed over. So, Okay, so let's start with a few examples then, and I'll start with the with the neutral impurity. Neutral impurity, by the way, I've given you a handout, so please read through. I'm kind of following some part of that now. And so I will, because you have the handout, I don't want to kind of derive every small little thing. I'll just kind of point out a few things. But I'll discuss the things that may not be apparent in the handout. So a neutral impurity is how do you form neutral impurities? For example, let's say you have a donor atom sitting in a crystal of silicon, where you have normal silicon atoms, and then one of them is a phosphorus atom, which is a donor. It's not the best example, but let's say the donor level is rather deep, meaning here's the conduction band edge, here's the valence band edge, and we have discussed a little bit about donor levels. If the donor energy level, if the quantum mechanical energy state or eigenvalue of that extra electron that came with this donor atom is very close to the conduction band edge, then room temperature can easily ionize it. It will kick it in, KT, that electron will get hit or will absorb an optical phonon, for example, and just or a room temperature vibration from the lattice, and it'll just get promoted into the conduction band, in which case it's now on the highway. It can zip past and move around. It won't be tied to this, but that would be a charged impurity, not a neutral impurity, right? On the other hand, I may have certain defect states that are very deep. I may have a defect state that's maybe 10 times KT at room temperature. Maybe that's 260 MeV, right? In which case, the amount of I'll have quite a few of those, let's say, and the number is Ni. The density is Ni. You can see that only e to the power minus this energy, roughly, or the order, that fraction will be ionized. E to the power minus 10 at room temperature. That's negligible. I can forget about it. I say all of them are unionized now, right? And in that case, I have this many impurity atoms sitting there, and the electrons are actually tied to that, right? But that impurity is clearly has broken the crystal symmetry. It's not the same atom as everything else. There's a slight difference in the potential. So if a mobile electron in the conduction band comes along, it says, well, it's silicon, 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 and suddenly, oh, there's a deep acceptor. So the potential it sees is, if you might, it's silicon, silicon. This is very approximate. I think the potentials look, quite a bit different. And then maybe it sees, something slightly different. Does that make sense? It's a localized perturbation, And so this is a small little change to the normal crystal potential. And that's what we are saying, the difference from the rest is what we're calling as our scattering potential. Right? And the best way to model scattering potential like this, it's very importantly, it is very localized in space. It's of the order of a lattice constant, one lattice constant. Okay. So what we say is there are two ways you can write it. You say, well, I'm going to give it a certain strength, which is the height of this thing here, W0. Maybe one can calculate that number more exactly using DFT and all that sort of thing. But it will come out to be maybe, an electron volt or 0.5 eV or something like that, order of magnitude. And I can say that it only extends a certain distance in real space. So you can write it as, this Heaviside theta function, a unit step function, which with a certain extent of R0. It has a radius of R0 over which it's acting. So if you want to look at the conduction band picture, I have basically like a little cylinder sitting in the path of the electron with a height of W0. And here's your conduction band profile EC of R, right? Does that make sense? I mean, just a little box sitting there, and your electron wave is coming along, right, as a plane wave, e to the power I, k dot r, 1 over square root of volume. That's your wave function of the incoming electron. Right? And then the question is, how is it going to scatter, and what is the rate? Right? That's the idea. And basically, as far as I'm concerned, I'm done with the problem because I've identified the potential. Everything else is basically just plug and chug now. I mean, you put it into the golden rule and calculate your scattering rate, right? and then go ahead and apply your Boltzmann and find your average scattering rate and find the mobility from there, right? That's all. So here's one way of doing it, and then you can. I think you are doing this problem in your assignment, actually, even to make life easier, you can even kind of approximate it. So you can perhaps imagine that if your wavelength of the electron is much larger, it is much larger. We talked about the de Broglie wavelengths. It's in 10 or 100 nanometer range, whereas this is a few angstroms. It's really like a point scatterer. It's very extent in space is not much. So you can also model it as some strength times the Dirac delta function. That's even easier because when you do Dirac delta, you don't have to evaluate the integral. It makes life easier a little bit. So just the units might change here. This unit would be in electron volts. If I put the strength here, what will be the units here? I think you should be comfortable. So Dirac delta has units of 1 over its argument. And remember, this is a three-dimensional vector, r. So it's 1 over meter cube or centimeter cube. So this will be in eV times centimeter cube, right? And this is 1 over centimeter cube. So essentially, whatever is your scattering potential should have units of energy in the end, right? So, and what is this S if I were to model this, for example? The strength is the height, right? And the height times its volume, right? Does that make sense? It's the height times volume. I plotted in a 2D picture, but in a 3D, the volume is just 4 over 3 pi r naught cubed, really, right? So your W naught times that is what your strength should be if you want to make your life a little easier and calculate it in this way. 2 parameters, height and the spatial extent. That is enough for this point scatterer picture. So once you do that, I'm not evaluating it for you. Your end result for the mobility will be something like this. You'll be inversely proportional. So I'll just write this kind of the format that's given there is nice because it's you can actually basically just plug in the numbers and get the answer right away. This is the formula. There's a Bohr radius. There's a Planck's constant here. There's a dielectric constant of the semiconductor here. And effective mass, E. So the mass is actually up in the numerator, and the density of impurities. The density should be in the denominator. The more is the density, lower is the mobility. That's not hard to understand. The effective mass, and all you can think a little bit about it. It's saying that a lighter mass electron will actually have a lower mobility here, and that is related to wavelength and all that sort of thing here. And you can think a little bit about why. And once you plug in these numbers, Bohr radius, Planck's constant, all that stuff, what you're getting here is this formula that gives you the mobility in numbers that you actually measure experimentally in centimeters square per volt second. And for example, for germanium, electrons in the conduction band of germanium where the effective mass is 0.12, so that is 0.12. Dielectric constant is 16, relative dielectric constant. And you plug in these numbers, if you have 10 to the power 17 per centimeter cube neutral impurities, so this is 10 to the power 17 per centimeter cube, you get a mobility of about 1,000. So that means this, and if you actually measure a high quality germanium crystal today at room temperature, your mobility is actually quite a bit higher than that. And that tells you right away that you must have much less than this much neutral impurities. Does that make sense? I mean, yeah, that's so you probably have the germanium mobilities, I forget exactly, it's a few thousands for sure at room temperature. So there's one. Yeah.
Just to check, that theta function has the Heaviside step function?
It is, correct. And the way it's written here, yeah, it is the Heaviside, and the R is depending on the dimensionality. If it's 3 dimensions or 2 dimensions, you just take care of that, X, Y, or yeah. One of the important characteristics I wanted to mention is when you do the scattering rate evaluation, you'll see that the scattering rate, or rather the, maybe I can appeal to some of our earlier discussions here and ask a few questions because this we want to. So in real space, or let's draw a bigger picture for that. So in this problem, in the real space, the extent of the let's call it x. It could be 3 or 2 dimensions or 1 dimension. Doesn't matter. And what I'm going to plot here is the scattering potential in the after you have the matrix element, which is basically an integral of your scattering potential in real space, e to the power iq dot r, and there's a volume and all that. I think we had derived that. So it's the fact that the term that enters your golden rule is just a Fourier transform of the real space scattering potential. And here I'm going to plot it. What is q here? It's the initial momentum of electron minus the final momentum. The magnitude of that. How much did the momentum change? Momentum is a vector. So if the electron was going in this direction, and then it scattered because of this obstruction, and it started going in that direction, that's your k prime. So you have initial vector and final vector, and there's a difference between the two, right? And that's what we're calling as k prime. And this vector here is what we're calling as q. The magnitude of that is just the length of it, right? So, okay. Yeah, let's call it r in general. So in 3 dimensions. Okay, this is q, and what I'm going to plot is w of r and w of q. So what we are saying is for the point scatterer, the w of r is very sharp in real space. It's kind of like that, right? So the distance here is very small. I think you can see right away that means in q space it should be really spread out, right? It should be really spread out, because the more I go to close to a lattice constant, this is just a Fourier transform, so it will probably have very small dispersion. If this is extended out a little bit, it will become a little more localized. But in general, what does it tell you? It tells you that a point scatterer has, it can put an electron, or it can dephase or scatter an electron from a state k to all regions of the Brillouin zone. It can change its k by a large amount. That's what it's trying to say. It can go very far in k space. It cannot change its energy because it's a time invariant scattering mechanism, but it can go very far in k space. In fact, this is important because if you look at some materials like germanium or silicon or graphene or molysulfide, these things have multiple valleys, not just one valley. So and a point scatterer can also scatter all the way to the other valley too, inter-valley scattering. Because of this reason, it's localized in real space. It has a very broad reach in k space. It can go inter-valley, large k values. And this is not true for ionized impurity scattering. We'll see it has a very short reach in k space. It cannot scatter very far. Is that at least qualitatively clear? And then when you calculate it, this is what comes out. Okay, so the next is ionized impurity scattering, and I think the process is now very similar to what we just talked about. You identify your potential again for ionized impurities, and the ionized impurity picture is, let's look at the shallow donor. That's a good example of an ionized impurity now. Right? A shallow donor would, on the other hand, be somewhere here and has lost its electron, but that means it's charged with one positive charge, or maybe it's a double donor, for example. It can have +2 charge, or it can, if it contributes 2 electrons, if it contributes 3, it's +3. In general, it's Z. Z is the number of how many electrons did that donor give you into the conduction band. So Z, and so the charge as a result of an ionized impurity. So the idea is the potential that you would see because of that in real space would look something like this. Okay. This potential, which is what I'm plotting, is the variation from the flat band condition, the change, the perturbation to it. Okay. So W of R is going to be Coulomb potential. So Z is the number of charges that came from there. E and remember, this is the potential seen by electrons. So it's a net charge times over 4 pi epsilon of the semiconductor dielectric constant of the material medium times 1 over r. Right? That's the Coulomb potential. Right? If an electron is trying to move around here, it will get attracted to this positive charge, and that's the potential. Negative means it will be attracted. And but in most solids, what we see is this is not quite exact. The reason for that is there is not just one electron in the solid. There are lots of other electrons in the conduction band, and as a result, what happens is they can just like I think the classical analogy is very apt here. That if you have a lot of electrons, you can really screen all changes of the potential because electrons are free to move around in the conduction band, so they can screen it. And that screening, I'm not deriving it. It comes out from like 2 steps from the Poisson equation. That the screening length, the length scale over which they can the electrons can screen. You can imagine the screening processes that electrons will come in. Some electrons must have very short wavelengths. Some of them a little longer. Some of them a little longer. So there's a combination of various wavelengths of electrons that are needed to screen it. But once they screen it, the potential becomes e to the power minus, so it gets damped out by r over a certain length, which is the Debye length. This is called the Debye length. And this potential, actually, before it was used in solid-state physics, came from atomic physics, called the Yukawa potential for mesons, pi mesons and subatomic physics, but essentially it's a Yukawa potential, but it works for charged impurity scattering in semiconductors. The Debye length is given by dielectric constant times the kT over q square times the mobile electron density, square root. So this is the Debye length. More is the electron density. Smaller is the Debye length, meaning your screening length is much more effective. Screening is very effective. More are the free carriers, screening is more effective. So, and you can calculate roughly what is the order of magnitude of the screening length and such. Okay. So here's the potential that is used for calculating ionized impurity scattering. Now you can see the integral you need to evaluate is of the form e to the power minus r over r, again without constants, and then this is your potential form. I mean everything else is a constant here, right? And then when you calculate your W of q, you must integrate d cube r, and this times e to the power iq dot r, right? Okay. When you do that, I'm again not doing this for you, but you can evaluate this out. You can get the exact integral of this. The answer is actually kind of simple. So the answer in the denominator, which is what I'm really after here, goes as q squared plus 1 over the Debye length squared. And there's some stuff sitting in the numerator, which is all this bunch of constants. Well, okay. So z e squared by epsilon and all that sort of thing. By epsilon s and all that. Okay. So here's your scattering matrix element done. Okay. And I wanted to discuss a little bit about this because you can look at this and compare it with the point defects. Compare it with the point defects. Here, Q, because these two scattering mechanisms are not changing the angle, not changing the energy, you can actually write from here that K prime squared is K squared, this is a triangular triangle identities, and K prime squared is equal to K squared plus Q squared, I forget, minus probably or plus, yeah, cosine theta or something like that, right? Something like that, yeah. So, and if the kinetic energy is not changing, if you're just changing the momentum, this is a elastic scattering mechanism due to Coulomb impurities, then the q squared. So essentially, what you I think this should be sine theta, right? Is that correct? Is it cosine? Okay, cosine then, yeah. So from here, what you can basically show in one step, I'm just skipping that, is 2k, sine theta by 2 or something like that from using the half angle formula of it. So q is roughly 2k times sine theta by 2. You can physically see it probably here. So, yeah, that if theta is small, you get k times theta, right? Theta is small. The length of this arc is just k times theta, right? So, yeah. So you can see now that I can write this as it says as sine square theta 2k LD. Okay, sine square theta by 2 over 2k LD. Okay, so I'm just kind of renormalizing this whole thing and writing it in a fashion that I want to plot, and then I think the k square is a 1 over k square that I pulled out of this whole thing, right? Just to kind of see the angle dependence of this scattering event. And when you let's look at it and compare it to the point defect scattering. So for Coulomb scattering, even after screening, your scattering potential really has a very large reach in real space. Its Coulomb force is long range. Debye screening makes it shorter range, but still, it's actually quite a bit longer. Many lattice constants, many atomic lattice periods, not just 1 or 2. Right? And as a result, the scattering potential. Actually, I shouldn't be plotting it in this way. I just want to plot it as a function of q. So let's plot it mod q. I don't want to confuse you with what is going on in the negative q here. The way we have defined it is just absolute value. So let's just plot it like that. And for the Coulomb potential, then maybe I should just use a dashed line for it, just to not confuse everybody. So the Coulomb potential. You can see that it will start out. Here's what we're trying to plot, and it starts out at a certain very well defined value when yeah. So from here you can see this is the factor. Q is sine theta by 2. So it goes as 1 over q squared plus this. So essentially it kind of goes like that. And so that's Coulomb scattering potential because that's going as 1 over q squared plus something squared. Makes sense? And that something squared is really 1 over the Debye length squared roughly. And so the extent, in real space it goes out by a certain length, which is given by a screen Coulomb potential. In the k space, the reach of it is roughly of the order of 1 over the Debye length. You can see that, right? So that means that the Coulomb potential will heavily, scatter with small angles. The scattering rate is very large because scattering rate is proportional to the square of the W, right, from golden rule. But as you go to larger angles, Coulomb scattering is not effective. It cannot dephase the angle by that much. That's the physical meaning of it. Yeah.
Say in k space it goes, it's 1 over the Debye length. Those units are different though.
So yeah,
no,
you're right. Yeah, 1 over length.
Yeah.
No, that's right. So so this is 1 over length. So it's q is 2 pi by wavelength. So right, correct. Yeah. So physical meaning of it is Coulomb potential is not able to scatter by much, and therefore it heavily favors the forward angle scattering, meaning a small angle scattering. So it will create a beam of electrons with a small angular spread rather than all kinds of spreads. So that's the physical meaning of that. And I think you can see right away that when I take this and I go back and find my quantum scattering rate and classical scattering or momentum scattering rate, there's a large sine theta factor sitting out there because of the scattering rate here, right? And therefore, the momentum scattering rate will be quite different from the quantum scattering rate for this particular scattering event. And that's also experimentally very much measurable, and people have measured it. Okay, so I would say that when you do the integral for your assignment, this is not the end, because then you have to do the all final states integral, meaning you have to integrate over all q, and you will see that in the denominator there will be this factor that will appear, and the integral will be undoable analytically. So, but then you can look at this factor carefully and you'll realize that this is very slowly varying. It doesn't change much. You just make it a constant and pull it out of the integral, and you get the final expression for the mobility as a function of the impurity density and all that. It looks a little, too many factors here, but I think most of them should make some sense. Mobility is again inversely proportional to the number of or impurity density. More is the impurity, Coulomb impurity, the lower is the mobility. It's inversely proportional to the square root of the effective mass. Lighter is the electron effective mass, higher is the mobility. For two semiconductors with the same impurity density, the one with the lighter mass will have a higher mobility. That's it. More is the dielectric constant of the semiconductor, more is the mobility as a square. Right? And that probably should also make sense, because the dielectric constant of a semiconductor sits here, so that damps the scattering potential. Right? The more is the dielectric constant, weaker is the perturbation, because in the denominator, and it indeed goes a square of that term here. And so on. And then there's a temperature dependence, which is like a 3/2. When you plug in all these numbers, electron charge, effective mass, dielectric, of the chi here is epsilon 0. I think there's just some unit. Laws of physics are invariant, but not what people use as units and symbols. So that's just epsilon s and epsilon semiconductor and epsilon of the permittivity of vacuum. So when you plug in the numbers, here's what you get, and again you can plug these in. I just wanted to kind of show any questions. Show a few of the numbers here before we start discussing about phonon scattering, which I think should take the rest of the class today. So if I just plug these in and look at neutral impurity scattering, just orders of magnitude. Here's a plot. I just whatever formula I just showed you there. And also I think is derived in your book. Here's a number. Here are some numbers. You recognize this formula. And what I've chosen here is an effective mass. You have to choose these things. What is your effective mass? So I choose 0.2. 0.2 effective mass is typical of silicon conduction band or gallium nitride. These are effective mass of 0.2. And the dielectric constant I've chosen as 9, the epsilon. And you can see that if my impurity density is 10^17 per centimeter cube, my mobility that I'm calculating using this is of the order of 2,000 or something like that. And if you go at 10^18 per centimeter cube, you really get hit by impurity scattering. It goes down quite a bit, from to 300 or something like that. So now charged or ionized impurities that we just talked about, we look at that. I told you there's a little more involved, but if you have a hard time doing the integrals, just ask Mathematica to do it. It will give you the answers very nicely and not complain analytically, so you can use that. And here's this expression that we just talked about, and you can make a plot of this whole thing. And here's a mobility as a function of ionized impurity density now, just a plot of that formula. Okay, and what you're seeing here is I've plotted it for I think two ionized impurities, two kinds of semiconductors. One of them has what am I doing? Okay, so one of them I'm just plotting it as an effective mass of 1, the other as 0.2. So let's just look at this one, ionized impurity scattering. And there are actually two formulations of ionized impurity scattering. I think that's what I've done here. Mu ionized and d 0.2. Okay, yeah. So the two formulas. One of them is at room temperature. The other is at 77 Kelvin. So there are two. And there's a little bit of turnaround because of that logarithmic factor and all that. But just let's look at the order of magnitude. So if you're 10^16 per centimeter cube ionized charged impurities, your room temperature mobilities would be maybe about 20,000 or so, 20,000 centimeters square per volt second. And if you are at lower temperature, it will be well, okay. So it's somewhere around here. These are the orders of magnitude, and this is 1 over impurity density. The order. There's a little change here because screening kicks in and all kinds of other things happen here at high doping densities, but at relatively low doping densities, it's a very good approximation and it works well. Okay, so all right, and so I'll talk about just to kind of remind again, the nature of the two scattering mechanisms are different, point scatterer versus ionized impurity scatterers. This is an important point here. Okay, let's look at phonons now, because that's one thing that no matter how pure I make my semiconductor, I cannot get rid of this scattering mechanism. And this is why it's called an intrinsic scattering mechanism, because it's not dependent on how many impurities they have in the semiconductor. The purest version will still have the full strength of the phonon scattering at play. You can't remove it. And the phonon model that we use, I think how many of you have done this, some sort of a derivation of the phonon models in acoustic, optical, or how many, who has not seen it? Okay, so I'll just briefly go over it because that's like a few classes to itself if you want to go over it in detail. But the basic idea is that if I take two atoms with the nuclei and then the electron clouds around them, right? And then I try to, let's say they're very far apart, R is very large, and they're not interacting at all because they are both charge neutral, and the electron wave function here is only about a few angstroms or 0.5 angstrom, and that's also 0.5 angstrom. They're really not seeing each other at all, right? And so if I were to write what is the energy of this whole system of two atoms, they're very far apart, then this is kind of the total energy of the system. Everything included, the fact that this Coulomb interaction put very small repulsion between the two electron clouds and attraction between the electron cloud and the nuclei and all that. You sum everything over, right? And there's the total energy of interaction between the two of the whole system here. We are not talking about the nuclear energy at this point, just Coulomb energies and exchange and all that sort of thing. Essentially, it's negative, very slightly negative, and that negative part is what's called a van der Waals interaction. It's very far apart. So van der Waals, who was actually the advisor of the person who discovered superconductivity, Kamerlingh, his whole philosophy in life was that matter will find ways to attract, and that is the whole philosophy of life. I mean, he proved why atoms which are very far apart, want to form bonds. Essentially, that's why we have a whole class of solids, van der Waals solids today, right? Which are two layers which are completely charge neutral, but there's a weak force between them of attraction. And so this little negative part is van der Waals energy, right? And the reason for that is everything can be pictured as a little dipole, and there's a dipole-dipole interaction between them. And then if they are plain charges, so meaning charged, charge neutral materials will find to attract. So there's a negative part of it. But then as you bring them closer up to each other, I think you can see that this. What happens is the attractive force wins out over the repulsive forces when you bring closer. And you can write this whole thing down, and it will kind of drop, meaning you can gain energy if these two atoms are closer to each other. But then if you get too close, then the electron cloud here and the electron cloud kind of start interacting with each other, and they realize, oh, there's Pauli exclusion and all that sort of thing. They kick in, and so it kind of goes back up. It repels. They can't be too close. So this is the general nature of all atoms and forming bonds. This is why hydrogen, nitrogen, or oxygen, they all, instead of being individual atoms, they have their chemical bonds, right? And the bond length is roughly here. That's the bond length where you have the minimum of the energy. Right? It's the length of the bond. And if you go slightly off, then you have to pay that little energy cost. And if you zoom in here, this picture here, the bottom of any curve is a parabola. Right? If you kind of zoom in there, and that you can write as u around that minimum point R naught is roughly half some spring constant times R minus R naught whole square. Half kx squared is the mass spring system now. Right? Does that make sense? It's just model it like that. You can really calculate it from the atomic principles of electron attraction and exchange and all that. What exactly is this constant? But I think you can kind of also ballpark it very easily by looking at these numbers. So this is how any chemical bond forms. And now if I take it and I kind of try to stretch it, I shine a laser on it, and then I can this is a harmonic oscillator. I can see it will have Raman modes, it will have vibrational modes, all that stuff. I can see this. This is really a quantum mechanical system in that sense, and you can observe all of that. Okay, so that's that. Now instead of just 2 atoms, we are in a crystal, so nothing really changes much except I have a periodic array of these atoms now. That's all there is to the. And the phonon, in a 2-atom molecule, there are no phonons. I mean, a phonon is a wave. Wave has to go and has to have a wavelength and all that. So essentially now, if I have a series of atoms and the mass spring system, like here now, right? So we already discussed that. And you can imagine that if all the atoms are the same, and I take one of them here, and they're all sitting at a certain lattice constant, they're all at equilibrium, there's no vibrations. And I take one of these and I just, maybe move it a little bit to the right and let it go. And now you can see that will, push that one, that will pull this one, and that will push to the next one and all that. So there will be a wave that will propagate now in the whole lattice. It's not obvious, but once you write down the equation, you'll see the wave is the solution to this equation. But once you have a mass spring system, and this problem is going to actually become a little important later because we are going to use it to develop ideas of superconductivity and also this operator formalism and all that, because but anyway, this is the classical picture of it. So there can be actually 2 kinds of waves, and let's just look at the first one first. Here's one kind of wave where if the vibration, so for example this atom is not vibrating, S is the index of which lattice point you are in. And so I can write that for this mass spring system, the force on any atom, or any mass, is equal to the mass of that atom times the acceleration, d2 over dt squared. And what is this small u? Let's not confuse this. Okay, so this was energy. Let's forget about that for a second. This small u here is the displacement from its equilibrium position. Okay, so you can equally write it as its original equilibrium position, let's say x0 minus small u. Does that make sense? I mean, original position minus, but x0 is not changing. So I'm just interested in the u, the variation or the displacement. Am I writing u of s? Okay. So instead of writing u though, I can write it as which particular, I have an index, I have an integer index of which sites here, right? So I can write it as u of the s site, of the s site. So the displacement of the atom on the s sitting on the s site, the mass times the rate of change of its, x coordinate is this Newton's law, right? Mass times acceleration. And that must be equal to the spring constant c, which is given again by the curvature of this thing here, right? The curvature of the mass spring system. Spring constant c times the, s, let's say, s minus of s plus 1. So, or s plus 1 minus s. So if I am looking the one on the right and one here, what is the change in the 2 displacements, right? The change is very important, because if there's no change, the spring has not changed its length, right? Does that make sense? If the displacement, sometimes it's confusing because the picture I'm showing is a longitudinal picture, but let's say I'm plotting the magnitude of u of s, or and this is your x. If all of them are displaced by the same amount, if every one of these are displaced by the same amount, do we actually have any stretching or straining? No. That means I've moved the crystal from here to there, right? There's no internal strain or stress or anything like that, right? So only when you have a difference, you have a force on these. So essentially, if one of them is a little bit larger than the next one, for example, then I have a force between them. And in fact, this is what we're trying to say is this: the amount of displacement is going to become a wave. And essentially, of s plus 1 minus E of s is the displacement of, to the right, and then to the left is, something like that, right? Or s minus 1, I think, yeah. So this is your, stretching of the spring length to the right, and this is to the left. Right? And now you have to solve this equation, and I think it's pretty clear one should make an assumption here, or try the fact that is my displacement a wave, or is it, so or not, and from this equation you can take a guess that it is going to be a wave, and of the form us is equal to u0, which is the amplitude. A wave is always e to the power I, q times x minus omega times t. Right? Just try that. What is the x? X is just the index s times the lattice constant a. These are the points at which the atoms sit. This is the x coordinate, so minus 2 times a, minus 1 times a, 0 times a, and all that. So that's just your x. So you try this here, plug it in, and you will see from here that on the right side, first of all, on the left side, you see you have a double time derivative, right? So that's just going to pull out 2 times I omegas to the front, right? It's just going to pull out I omega squared. So I get minus I omega whole squared on the left side times the mass and times the u, right? Is that clear? I mean, on the right side, I get c times, again, all of them have this constant value of us here, right? And these things, for example, you see here, what I get is e to the power iqa, because the s plus 1 e to the power iqa. This is just, let's call it 1, and because they'll all cancel in the end. And this is also 1, and that's e to the power minus iqa, because it's translated to the left. Right? So what you end up getting here then is basically this and this will give you 2. You get a 2 cosine of qa minus 2. And you can flip this all around. Your amplitudes and all will just cancel, and you get your phonon dispersion from here. Yes, a wave is one of the solutions that is possible for this sort of a phonon mass spring system, and the omega of q from here, if you rewrite it, you get 2c over m times 1 minus cosine of qa. Omega squared will look like that from here directly. So this is your phonon dispersion only for the acoustic modes. So yeah. So if you find the omega though, it will be square root of this, and that happens to be like twice sine square qa, so it becomes like a sine of qa over 2. And I think there's a square root of 2 or something that okay. There are 2 here again. Okay, so this is the idea. So and then the absolute value, taking square root of this, and then if you plot it, here's your sine qa of a phonon. These are for silicon acoustic phonons. Now you see there are 2 kinds. There's a TA and then there's a LA. And the TA is a transverse acoustic. Transverse acoustic and longitudinal acoustic. The picture shown here, you see the atoms are vibrating in the same direction that the wave is going. The wave is going along the x-axis. And the atoms are also vibrating in the x direction. Right? So that's called longitudinal, when the vibration is along the direction of the wave propagation. Or in other words, when your u is the displacement is actually a vector, right? When it is parallel to q, which is the vector in which the wave goes, then it's a longitudinal. If the atoms were vibrating, the other way, this way, right? When the wave is going that way, that would be transverse. In other words, u would be perpendicular to q, would be transverse acoustic wave. And I think I had a picture. Yeah, that's the picture. This is a transverse acoustic wave. Here's a equilibrium. Here's the longitudinal acoustic wave. I actually have 2 atoms here, but and do you see why longitudinal will be larger than transverse? From just looking at these 2, you can see the distance between the 2 is has not changed as much as here, right? So you're really a lot more. It takes a lot more energy to create the longitudinal, because the distance variation is the highest in some sense in between the two. Whereas here, the vibration, it has moved from its original state, but this bond length hasn't changed as much. That's why it's always true typically that the LA will be always larger than the TA mode's energies. And these are experimentally measurable and such things. Okay? And the other thing I want to say is here we assume that there's only one type of atom, right? Only one type of atom. All the atoms are the same. But in many semiconductors, gallium arsenide and such things, you actually have two kinds, right? Gallium and arsenic. So what happens is, in addition to this acoustic modes that we talked, we also have the optical modes now. And that also comes out by just taking the 2-atom basis now. Right? And the optical modes are when the nearest neighbor atoms, this and this, they are always in phase, meaning if this one goes to the right, that goes to the right, left, and so on. Right, and so on. So this is a acoustic mode. Similarly, if this goes up, that goes up, that goes up, and so on. These are in phase. This is opposite. If one goes up, the other has gone down. If one goes to the left, the other is going to the right. So that's optical modes. And they will also have longitudinal or transfers, LO and TO. So these are all the modes. You can see perhaps that this would be larger in energy, but I think we're out of time, so we'll discuss this a little bit, finish this up in the next class. But the LO modes are typically the strongest scattering mechanism for compound semiconductors. This is the mode that dominates everything at room temperature. Acoustic modes are also very important, and we'll see in the next class how to kind of calculate their Ws and all that. We're almost there, actually. So yeah. Okay, good. So we can stop here and continue on Thursday then.